Cool. So yeah, I'm more of a topologist. And I guess I was trained more as like a computational topologist. And so I guess I'm going to do a little bit of proselytizing about computational topology and step back for a second for maybe, well, more for like 10, 15 minutes, give you a little overview of computational topology, in part because I feel like, topological quantum computing is super cool. But if you drop one of those words, quantum, you just have topological computing. There's all kinds of stuff known there about computational problems in topology. And I think a really intriguing question is, well, okay, sure, quantum topology can do a lot for quantum computers. I think we kind of all agree with that, at least in theory. And it would be very interesting if quantum computers could do useful stuff for topology in the algorithmic sense, okay? And not just make topology much easier to justify getting grants from and stuff by trying at the quantum computing. So, but yeah, so let me give you this little intro to computational geometric topology. So it's a little bit orthogonal to the meat of the talk, but I want to take this opportunity to make you all think about these things. So what do I mean? Well, first of all, if we're going to do geometric topology, you have to pick a category. Do you want to work with smooth manifolds? Do you want to work with PL manifolds? Do you want to work with topological manifolds? There's only one right answer if we're going to do computational geometric topology, and that's PL manifolds. Okay. So the basic idea is we want to answer questions about PL manifolds. But not just answer them in the mathematical sense. We want to do it algorithmically.
For low dimensions, are they the same?
Yeah, we'll get there. Yeah. So, and moreover, if you're going to do things algorithmically, well, once you have an algorithm, you want to find the best algorithm. Yes, question in the back.
Yeah, could you revise what PL
manifold? It's piecewise linear. So, so there's really two types of questions I have in mind. And it's the first question. The first types of questions I think it's fair to call like the most important questions in PL topology, but it's the second types of questions that are important for quantum computing. So the two types of questions are basic decision problems. And I'm not going to give rigorous definitions of of this dichotomy here. I'm just going to give you lots of examples. And then there's computing invariance. So, all right. What's the one question to rule them all? If we're going to study PL manifolds, what do you want to do? You want to know, given two PL manifolds, are they homeomorphic or not? So that's the first one. Use example 1A. I'm going to pick a dimension, and we'll just work in a fixed dimension. So because the problem gets interesting if we do that. So this is a D manifold homeomorphism problem. And the input is two PLD manifolds, M1 and M2. And the output of the problem is yes, if they're equivalent, and no otherwise. So so what's a PL manifold? It's a type of simplicial complex that satisfies a condition on the links of the vertices. Namely, the link of every vertex needs to be a PL sphere of one lower dimension. Okay, and there's some fuzziness here. How do you know if I give you two simplicial complexes, how do you know that they're actually PL manifolds? That is itself a decision problem. And we'll piece together the answer in a moment. Okay. Let me note.
What does equivalent mean?
Yeah, so they share a common refinement. Their triangulations can be refined, for example, so that they're combinatorially isomorphic. maybe the easiest way. So, does that answer the question for you? Okay, great. So, so the size of M. So what is M? It's given to our computer, us, as a simplicial complex. So the size should be the number of simplices in the complex. So I'll just denote that lazily by the absolute value of this manifold. Well, really, it's the number of simplices. Right, because if we're, you can first ask, does there exist any algorithm to solve the problem? And then you can ask, well, what's the complexity? And that's going to depend on the size of the input. You want to allow the running time, for example, to depend on how large the input is. So, cool. So what's the status of this problem? Depends on dimension. If D is less than 3, this is easy. For example, if D is 2, I give you two triangulated surfaces. You want to know, are they homeomorphic surfaces? Well, you check if they're orientable, you compute the Euler characteristic, then you're done. Yeah, you can determine, are those invariants the same? You're done. And you can kind of see now why, computing invariants has some bearing on the first one, because you use invariants to distinguish things. So this is easy in the sense that, more precisely, there's a polynomial time algorithm in the size of the input, which if the input is 2 triangulations, it should be the size of the first triangulation plus the size of the second triangulation. So it's polynomial. Okay. D equals 3. What's the status of that? So in this case, there exists an algorithm. And the running time is something like the following. So this is some fixed height tower of exponentials. So this is a constant height. But I don't really know what that constant is. It's like 7 or 8, probably, maybe 9. So what's going on here? So this is kind of a folklore theorem. Modulo Perelman, modulo the geometrization conjecture. In some sense, apparently Thurston himself and Riley understood this to be true. If you took geometrization as fact, then it should imply that there is an algorithm to solve this problem. Okay. Yes.
What's the algorithm?
So I'll tell you in a second. Yeah. So now, so the existence of an algorithm is folklore, and then the actually getting an algorithm. This sucks. This running time is terrible, right? But at least you have some bound on the running time. A priori, there are problems that are computable where you can get no bound on the running time. Okay, so this is better than no bound. And so this algorithm with the explicit bound is due to great.
Does it take no time to tell whether 2 listings of the simplicial complex are the same? Simplicial complex.
Oh, like combinatorially equal? That's going to be at least as hard as deciding if 2 graphs are isomorphic, right? So if you just have one-dimensional complexes, and so that's not known to have a polynomial time algorithm.
So
even in the special case,
that's tacked onto this.
Yes. Yeah. So in fact, so I'll answer your question. What is the algorithm in a moment here? But this is some algorithm that has that running time. But in complexity theory, you can ask, is this the best algorithm? And sometimes you can prove that it is, maybe modulo conjectures such as P versus NP. But at the moment, we don't really have any good lower bounds. There may be way better algorithms than this. The only known lower bound to this problem in dimension 3 is graph isomorphism, right? So all we know is that the only other problem we can tell you where deciding if 2-3 manifolds is homeomorphic is at least as hard as that other problem is graph isomorphism, which is it's not a polynomial time computable algorithm, but Bai recently put it in sub-exponential time, right? And quasi-polynomial time. So it might very well be in P. So that might not be much of a lower bound at all. Okay, so maybe I'll give the kind of lazy geometers version of geometrization, and then I'll tell you the algorithm. I will not be proving this. It's Perelman's theorem. This is a flavor of it. So what it says is, given a closed, let's say orientable. Let's see, cover the unorientable case as well, that's fine. M3, so it's a triangle M3 manifold, or I'm not saying anything about algorithms in this theorem actually. There exists a canonical set of embedded spheres and tori.
Eric, I'm a little confused.
Yep.
It sounds like a graph has dimension less than 3.
So graph has dimension 1. It's not a manifold, but it's a simplicial complex of dimension 1.
Right, so
And
less than 3 you're saying is easy, so I just was wondering what the
I'm sorry, but that's for manifolds.
manifolds, okay, but it's not like a PL, doesn't count as like a PL manifold, I guess.
Oh, so a PL1 manifold is just a disjoint union of cycle graphs.
Ah,
You know that. So yeah. Sorry, I was a little confused.
I didn't quite hear the definition of.
Sorry, yeah, so an arbitrary graph is not a manifold, right? Unless it's going to be a manifold that only have every.
So it's a manifold with a simplicial presentation, was that the?
Exactly.
Okay.
To triangulate that. Okay, so geometrization says there's a set of spheres. I don't know, maybe there's K of them. That's embedded in M and tori. Such that the following holds. And these are canonical in the sense that they really only depend on the homeomorphism class of M3, such that the following is true. Each component of the complement of the union of all these spheres and tori. So I take M and I throw out all these spheres and tori. Each component is either Seifert fibered or hyperbolic. And moreover, and it's not just, it's a finite volume, like complete finite volume hyperbolic structure. So in particular, hyperbolic manifolds that have finite volume and are complete are actually entirely determined by their fundamental group, so that this hyperbolic structure is unique necessarily. So this is the less lazy version of geometrization tells you that on these Seifert fiber components, you can put additional geometry on them. But for algorithmic purposes, knowing it's Seifert fibered is usually good enough for getting algorithms. So what is Seifert fibered? It basically means you have a surface, but it's really an orbifold. And then you have a circle bundle over that orbifold. And the total space of that circle bundle over the orbifold, over the two orbifold will be a three-dimensional manifold. So this is an S1 bundle over an orbifold, over a two orbifold. And the point is, this is highly combinatorial. So, what are the possible two-dimensional orbifolds? Well, you just have to give me kind of an underlying topological surface together with some cone point data, and then that's enough to build this S1 bundle, and you go from there. So somehow the most interesting part of the theorem is hyperbolic. Okay, so what does this mean? This means there's a Riemannian metric on the manifold that has constant sectional curvature -1. Okay. So the theorem allows you to upgrade questions about topology to questions about geometry in a canonical way. So that means all of the geometric invariants you get from the hyperbolic geometry on these pieces are in fact topological invariants of the original manifold. Okay, so the algorithm, I guess I'm not going to write this, I'll just say, how does one get this? So I have two three-manifolds, they're triangulated three-manifolds. I want to decide, are they homeomorphic? So what you do is you iterate. So these are embedded spheres and embedded tori. And basically, you can search for them. You can combinatorialize what these tori and spheres look like with respect to the triangulation. So you just search through all possible sets of spheres and tori, and you cut. Every time you have a set of spheres and tori that's disjoint, you cut the manifold into pieces. You get all these pieces. But the problem is the spheres and tori you pick may not be the canonical ones that you need to define. So you're just iterating through all of them. And then on all of the pieces, every time you cut, you say, well, is there a way to make all of the pieces Seifert fibered or hyperbolic? And if you can, you know you found the right spheres and tori. So once you've done that, for the two different manifolds, M1 and M2 at the same time, you're cutting them up and geometrizing them. You just compare their list of pieces. And there's some gluing data you have to compare as well. But that's the rough idea of the algorithm. Yeah.
Also a unique set of spheres and tori.
Yes. Yeah. Yeah. This is maybe implicit in the word canonical. So it's also unique. Yes. Good question. Yeah.
Check editorially when moments are like this.
How to check what comment?
How do you check hyperbolicity?
Yeah, it's hard. You use the fact that every hyperbolic structure can be described by a map from pi1 of the manifold PSL2C, and the set of solutions there is an algebraic variety. So, right, that's of course a continuous domain, but there's discrete points on that you can describe as algebraic numbers. So you work with algebraic numbers, or you can do like floating point arithmetic as well. And as long as you have a homomorphism, something that looks close enough to being a homomorphism, you can guarantee it as one. So things like that. So, yeah.
Is canonical with respect to a Greek triangulation or?
No, it only depends on the homeomorphism type of the manifold. Yeah, that word's doing a lot of work right now. So yeah, sorry. Yeah.
Is it easier to check whether it's common computationally to check whether it's Seifert fibered? I would guess that might be easier than.
So
It's either or.
Yeah, so you're asking that he's asking the following question. I give you a triangulated manifold, and you just have to answer yes or no. Is it Seifert fibered? And I don't really know what the complexity of that is. Yeah, it's probably way better than that. But a priori, it might just be a tower of exponentials that's height 2 or something. But yeah.
So two manifolds are going to be equivalent if when you cut out the spheres, you get. I don't understand what these variants are.
Oh, well, you get invariance from geometry now, is what I'm saying. So is that so the
Yeah, that's the question. Yeah. So what are these invariants from?
oh, for example, volume. Every hyperbolic volume hyperbolic manifold has a volume which is some positive real number, and that becomes an invariant of this manifold M3. For example.
That's a complete set of invariants for a manifold.
Well, you need to know the full hyperbolic structure, which in general is complicated. So let me plow ahead and I'll say a little bit more about that. All right, so I guess I was supposed to continue with the status. I don't want to leave you hanging. So we're talking about this one problem. So what about d greater than 4? Anyone know the answer? It's undecidable. Yeah, uncomputable. So given two greater than or equal to 4, given two 4 manifolds, deciding if they're homeomorphic is not possible to do algorithmically.
What about d greater than? You mean d equals 4 or d greater than? I mean,
It can equal 4, d greater than or equal to 4. For any fixed d greater than or equal to 4, it's uncomputable.
So what does that exactly mean? I mean,
It means if you could decide if two triangulated 4 manifolds were homeomorphic, you could solve the halting problem.
If you have an algorithm that does that for any two.
Yeah.
Yeah.
right, so
Because if
You have an out.
and you two manifolds,
No, the
obviously.
point is to do it algorithmically.
Okay.
Yes. So if I had an algorithm that could answer the question for any two 4 manifolds you want to give me, I'd be powerful enough to solve the halting problem. And I ain't powerful enough
Is
to.
that then saying there's not some complete set of invariants, computable invariants for?
That's in particular, yes. Yeah. There's not some countable list of invariants.
Yeah, right, so there are invariants, but they're not enough.
Well, all right, sorry. That's right. There's no countable list of invariants. That'll.
So I suppose you were assuming already that both are manifolds.
Yes. So yes,
But otherwise you would be.
that's right. Right.
What's computed?
Yeah. I was assuming that they're. I'll bring that up again in 5 minutes. Yeah. All right. So this is uncomputable. This is like an old theorem of Markov. from the 50s. I think 54 maybe. Okay, so I think that's kind of all I want to say, other than these little remaining questions. That's all I want to say about this problem. Let me give a related problem, which is a special case. You might think of it as a special case of this problem. So this is D-sphere recognition. So here the input is a D manifold. Everything's PL. So it's a single D manifold, not a pair of them. And you want to output yes if this is PL homeomorphic to a PLD sphere and no otherwise. So what's the status of this? So again, when D is at most 3, it's even easier than the previous problem, which is already easy. When D is equal to 3, what's known is that this is an NP intersect co-NP modulo the Riemann hypothesis, the generalized Riemann hypothesis. So there's kind of 2 theorems here, really. So this is due to, well, who would it be? I guess Schleimer, kind of like, yeah, I guess I'll give it to Schleimer and Cooperberg and Zentner. So this is fancy sounding, but in particular, it's probably not NP hard to decide if a 3 manifold is a sphere, right? If it were, then the polynomial hierarchy would collapse, and people don't expect that to be true. So, and moreover, problems in here are good that are, you know, you can certify when the answer is yes, and you can certify when the answer is no. That's what this is saying. And problems in this intersection are actually good candidates to be in BQP or even in P. Okay. So maybe 3-sphere recognition is in BQP. I don't know. It's not. I don't really have any good ideas, but maybe it is. Yep.
The NP part does not rely on generalized Riemann.
No, it's the co-NP part. Yeah, thank you. Yeah. The NP part uses what's called normal surface theory. Yeah. The co-NP part uses the fact that if you have like a non-trivial map to a Lie group, you have a non-trivial map to some finite group, and making sure that that thing's small enough is where the GRH comes in. Okay, and now something fun happens when D equals 4. We don't know what the status of this is, in the sense that for sphere recognition, it's not known whether there's an algorithm for it. This is an open problem in 4-manifold topology. But now when D is greater than 4, it's uncomputable. So if you give me a single 5-manifold and ask me, is it a 5-sphere? There's no algorithm to answer. And this is also a theorem of Markov. So what is known in D equals 4, in fact, a preprint just went up to last night, Martin's answer, he whittled things down. So what is known is that deciding if a manifold is a connect sum of S2 cross S2s is uncomputable, but you have to ask how many summands. It was known that 12 summands was enough to get uncomputable, and he whittled it down to 9. So asking if a 4-manifold is a connect sum of 9 copies of S1 cross, or sorry, of S2 cross S2 is uncomputable. Which is cool because S2 cross S2 simply connect. Right? Okay. So this really is the bird's eye view, I would say, of computational geometric topology, the basic problem, 2 of the basic problems. Now let me start honing in. Yeah, maybe I'll talk about unknot recognition, right? So you can ask versions of this question where instead of given triangulated 3 manifolds, for example, you're given diagrams of knots. You're given 2 diagrams of knots. You want to know are they equivalent? There's something very similar known here, right? At least, okay, that's a slight lie, but we get an algorithm like this for knots. Yep.
That's my 5 minutes question now.
Oh, right, yeah.
So every group is the fundamental group of a 4D manifold.
Right.
So aren't you, are this not implying that you're solving the problem algorithmically, that even a group presentation,
Yes, that's exactly what you're getting at. That's how Markov proves these uncomputability results. He says that, oh, we already know deciding if 2 finitely presented groups are isomorphic. that we already know is uncomputable. So let me convert those finite presentations of groups to manifolds so that they're homeomorphic if and only if the groups were isomorphic.
Why then is the question mark there?
This is for the sphere recognition, which is analogous to asking, I give you a finitely presented group and you want to know, is it simply connected? Or sorry, is it trivial? Right?
It's decidable.
That is not decidable. But the problem is the reduction. When you no one knows how to reduce. So the input to that problem would be a finitely presented group. And you want to know, is it trivial? That's undecidable. But Markov's proof doesn't work in the dimension 4 case. We can talk more later. Yeah. Well,
You could also filter by that size index you mentioned at the beginning.
right, yeah.
So I mean,
if
it's
you
a
ever bound
version of all.
bound that, everything's just computable because there's only finitely many things once you bound that. Yeah. So yeah, these are all about how when that number is getting big,
Right.
there's no algorithm that can. There's no single algorithm that can work.
So in some finite tree physics world,
Things might be
worry about
okay.
this.
Yeah, maybe. Okay, so let me talk about invariance now. To give you some of the other examples. So I've talked about basic decision problems, but we can talk. So let me do maybe an easy one. So this problem will be, this is a little bit contrived, but we could talk about the non-triviality of the kth homology. And it's important here that K is fixed. So the input, the simplicial complex, it could be a manifold, I don't really care. Delta, and the output will be yes. If the, let's say the kth homology of delta with Z coefficients, homology, I don't care, whatever, is non-trivial. There's no otherwise. So the status of this is that it's easy. It's in P. Okay. So generally speaking, computing homological and cohomological invariance in low degree is always efficient. It's just, you know, the secret sauce is Smith normal form. When you have the simplicial complex, if you want to compute its homology, one way to do it is the Smith normal form. And you can do that efficiently. It'd be much easier if that Z were just an R. Then you just do linear algebra on the chain complex. And that's obviously easy. Okay, so that's a little bit of a contrived example, but it's maybe a good one to know. So let's do another slightly contrived one, but it's important for quantum computation. I'll call this non-triviality of the Jones polynomial at Q. And just maybe for the sake of this, I have to pick a value of Q, and I don't know, I'm gonna pick a 17th root of unity. Why not? There's a few roots of unity you don't want to pick for what I'm about to say, but so the input here is a knot diagram, which isn't some triangulated simplicial complex, something like that on the far left board. Some type of planar graph with kind of decorations at the crossings, right? So that's a finite data type. The size of one of those graphs, the size of a diagram, is the number of crossings in it. Okay. In the sense that that's a reasonable measure of size, because if I were going to try to describe this to a computer, it would take about 3, something proportional to 3 amount of data to feed it to the computer. So here's my input, and now for this Jones problem, the output will be yes if let's just say that the absolute value of the Jones polynomial of K evaluated at this Q is bigger than 10 to the 100, and it's no if this number is less than 10. Okay. And let's just say we're only ever given knot diagrams where one of these two things is promised to hold. And the status is that this is NP hard. So basically deciding if the value of the Jones polynomial is really big or really small, even if you're promised it's either really big or really small, is hard.
What about just the Jones on the specialization?
Yeah, that's even harder. It's also, if you want to compute the entire Jones polynomial precisely, in the sense that you want to know all of the coefficients of each power of q as an integer in binary even, then that's NP. Yeah, good question. The point being, if this is a very coarse approximation, you know, the value of the Jones polynomial at q, you might think of as a very coarse approximation to the Jones polynomial as an integer Laurent polynomial. And this very coarse approximation is already very hard. This is also due to Gray. So let me give one more example before I dive in to the rest of the talk. So this example, you know, I think this stuff might be a little bit related to kind of Nat's conjectures. You know, it's somewhat in the ballpark of Nat's conjectures about you know, can you prepare topological states using measurement and feed forward with a bounded depth circuit coming from like quantum doubles for non-solvable groups. Okay, so I'll call this question: does there exist an A5 quotient of a knot group? So I'll explain this. So the input is a knot diagram, like one of those over there. Okay, the output will be yes if the fundamental group of the knot complement I1 of S3 minus K surjects A5. Will be no otherwise. And then the status is that this is NP hard. Great. And the proof is basically to study the digraph-Witten theory for A5 and get a kind of topological universality of the braid and mapping of the braid. So
And this is only for, I mean, A5.
yeah, well, I could really put any I could replace this with any finite simple group. It doesn't have to be A5, but A5 is the smallest. It has to be a fixed finite simple group, but that's a bit technical.
And you fix the finite simple.
Yeah, yeah. If you allow me to pick the finite simple group, I don't know what the complexity is, because I could alter the target I'm trying to surject to make the problem easier. Okay, so great. So now I guess I'm going to do a kind of sudden about face after my introduction to computational topology is over, and these pictures will get used momentarily. So now the question here that kind of motivated the theorem I'm going to prove in a bit is, you know, hyperbolic geometry is very useful in three-manifold topology, generally speaking, both theoretically and as a source of algorithms. So the question I had was, well, can hyperbolic geometry be useful for kind of topological quantum computation? So maybe a little more precisely, we could ask, can it be used to speed up topological quantum computation? And I don't know, maybe we don't even want the word topological in there, just quantum computation. Oh, sure. Here we go. And the answer I give is a rigorous, I would argue a rigorous unlikely. Okay, so probably, so no, but I want to actually prove it. Okay, in some manner. So let me maybe kind of reiterate the motivations here. So the motivation, there's maybe kind of one motivation that comes from combining two threads of thought in three-dimensional topology. So there's really since the 80s, there's been two threads of methodology in low-dimensional topology. So there's this kind of thread one would be the kind of Thurston style stuff. So in particular, the geometrization conjecture. And then thread two would be quantum stuff. And it's interesting to know, when do these things interact, right? And to what extent do they interact kind of non-trivially? And maybe the most compelling thought for the relation between these two things, something called the volume conjecture. So the volume conjecture would unify these two things if it's true. Okay. So I'm not going to really prove, I'm not going to do anything with the volume conjecture, but it's going to get some background here for this question. So this is due to Kashayev and Murakami. So what it says is that if you have a knot, it's not known to be a theorem. But if you have a knot that's hyperbolic, and I may screw this up a little bit, there's definitely people in the room that thought about this a lot more than I have. Then the conjecture is that you can extract, so the hyperbolic volume of the knot from quantum invariance. So on the left-hand side, what am I doing? These are called the n-color Jones polynomials. They're generalizations of the usual Jones polynomial, and you plug in an nth root of unity. And you evaluate, this is some complex number, it has a modulus, you take the log of that modulus, and you take the limit as n goes to infinity. The conjecture is that that thing, which is entirely defined using TQFT stuff, actually just is. First of all, it's an invariant of K. It's not even clear that this is well defined, but it's supposed to be an invariant of K, in which invariant, it's the volume of the knot, considered as a hyperbolic manifold, which is an invariant. So if you believe, you know, whether or not you believe this conjecture, if you believe what this conjecture is implying, that there's some connections here between these two like modes of work in three dimensions, then maybe the question isn't so crazy. Then again, maybe the question just is crazy, but we'll have a precise theorem in a second.
Okay, can you just explain what a hyperbolic knot is?
Yeah, okay, great. This is a good time to do it. So yeah, maybe, so I'm going to write a theorem, and then I'll explain the board over there that I prepared. So I'll just give you the definition. So a knot K in S3 is hyperbolic. And this is maybe not a super satisfying definition, but it's hyperbolic if the complement of the knot, S3 minus K, admits a complete Riemannian metric of constant sectional curvature minus 1. And that's like, hopefully those words are okay. It's a little technical, but yeah. So, but this is hardly how people think about them. Yeah. There's a theorem, which is really a special case of the geometrization theorem that Thurston himself was able to prove. He proved a special case of geometrization, a case that the manifold is called Haken. But this is a special case. What it says is every knot is one of the following. It's either a torus knot, a satellite knot, or hyperbolic. So you can think of the first two cases as kind of like in the geometrization theorem, which I guess I erased at this point. You had to cut things up using tori and spheres. Like somehow these are the first two cases, and the third case is you don't have any tori or spheres, and then you just have hyperbolic stuff left over. So here are examples. So this is a torus knot. Why is it a torus knot? Because it emits a diagram that can be drawn on a torus, the standardly embedded torus in S3 with no crossings. Okay. So these two are examples of satellite knots. So a satellite knot is a knot where basically there's some I'm using torus in a different way now. There's a torus in the complement of this knot that is not parallel to the knot. So you can kind of see it. It winds around. Imagine this thing. It's like kind of winding around this thing. So what, this is I guess the double of this knot up here, right? So there's this kind of basically satellite means it's a knot that looks like it was made out of another knot. Okay, you take one knot and then you tie that thing up, and you're going to get this kind of non-trivial torus in there. So these can't be hyperbolic, and torus knots can't be either. But all that's left, what Thurston guarantees us, is that you have hyperbolic things. Okay. So it's this kind of arguing actually that is going to allow me to prove my theorem. I'm not really going to tell you an explicit hyperbolic structure on any knots today, except for this one as an example. And instead, I'm going to say, well, we can do things that guarantee we don't get any of these cases, and then we're only left with that case. Okay. So, but this is a famous example that Thurston himself discovered, and I guess Riley maybe independently, that shows you how to explicitly build a hyperbolic metric on the complement of the figure 8 knot. So what you do is you take these two tetrahedra, but you think of them now as geometric tetrahedra sitting inside hyperbolic space, where these points are infinitely far out on the boundary. So these are called ideal tetrahedra. And these should be the regular ideal tetrahedra that have the full symmetry group of A4. And then you glue them up in this pattern. You don't really need to understand it, but you glue it up in this pattern. And that'll give you such a metric on the complement. And that geometric structure is an invariant of the topology of this. Okay. So, right, all right, so now I want to claim, so I have a half hour, is that right? But half hour, okay. So another board, I want to say what I mean by topological quantum computation. Funnily enough, I don't think anyone has defined it in this workshop, which is fair. I don't know that, for good reason, because what I'm going to say is the old, it's the classic topological quantum computation that goes back to Friedman, Larson, Wang. And so what did they say? So for this, I'm going to fill this in. So stop me if you can't see what I'm writing. But so I'm going to fix maybe a unitary TQFT in a 2 + 1 dimensional TQFT Z. And then all right, what I really have in mind is some kind of Resheti contrived construction. And so I'll also fix a color or an object X. Okay. So then whenever I have a diagram of a knot, maybe it needs to be a ribbon knot, right? And it needs to be oriented ribbon knot, but I can color it by that object X. And the TQFT gives me an invariant, right? Some complex number, it's an invariant. Okay. So what Friedman, Larson, Wang showed is that you can always approximate this complex number, the invariant of this knot, on a quantum computer. Okay, so over here, this is just a little cartoon of a quantum circuit. Okay, so a quantum circuit, these are a bunch of unitaries, all these UIs, they're unitaries on a pair of qubits, right? So each of these strands represents a qubit. You should read the diagram from bottom up. And in particular, when you do a quantum computation, you can always kind of assume, if you're doing things in BQP, you can assume that the computer's initialized so that the input qubits are all in the 0 state. So what they said was that, well, okay, given this, you can prepare a quantum circuit so that the following happens. If you input the all 0 state to this quantum circuit, and then you measure the output in the all 0 state, the resulting amplitude will be proportional to the quantum invariant over here. Okay. So, get my so in particular, you might interpret the probability, there's an amplitude here, which is taking this state, acting with that unitary, measuring against that. You can interpret that as once you take its norm squared, as the probability that this quantum computation outputs yes. So, so what they said was that you can convert this to a circuit so that the probability that this circuit over here, I call this circuit C, the probability that C outputs yes on input 0. What they said is that it's approximately and equal to the value of this diagram's invariant. So Z is my TQFT, X is the object, so Z sub X gives me an invariant of knot diagrams. So what they said is that this invariant, you square it and divide by something else, then this number becomes that probability. Okay. So there's a lot of work being done in this denominator, really. But the point, what they interpreted this as was as an algorithm to approximate this invariant. Because, okay, how do you approximate this invariant? Well, you run that quantum circuit and you run it 100 times and you ask how many times did I output yes? Then that number will be approximately this ratio. So then you can back out the numerator, but just by clearing the denominator. So the denominator, though, itself depends on the diagram. Okay, so this diagram here, there's this G here. I haven't told you what that is. What it is it's like the Platt index of the diagram. So this has 1, 2, 3, 4 Platts here. So what happens is you do get an algorithm to approximate this number using this, but it scales poorly with the width of the knot diagram. Okay. So this is kind of technical, but this is what Friedman, Larson, Wang did. Okay. Or Friedman, Kataev, sorry, this is Friedman, Kataev, Wang. So you can always do that for any unitary TQFT. But the cool thing is, for what I would argue, like the original picture of topological quantum computing is that sometimes you can go backwards. Sometimes there are TQFTs Z and objects X, where instead of converting a diagram of a knot to a circuit, you convert a circuit to a knot. Okay. And that, I guess, it's not true for, so this is sometimes, maybe I should make this dotted. And so what Friedman, Larson, Wang showed is they found a Z and an X where you can go backwards. Okay. So that this approximate equality is true. Yes.
Is it important that it is in the Platt representation, or is it?
No, not particularly. Any diagram you can quickly put in a Platt representation, but this parameter here will be important. Yeah.
What is output means yes?
Well, a quantum computer is a type of probabilistic computer, right? And if we're in this amplitude, you can interpret as a probability that this calculation outputs yes. It's just formal. You might read it as like, this is the bit that's being output 0 or 1. And if it's being output 0, well, I guess maybe I can make that a 1. Okay, so that means it's output yes. Okay, and you have all these zeros here because you're doing on computation or something. So yeah, they use UQSL2 and we're able to go backwards here. So, so really my question is, when we go from here to here, what kind of guarantees can we make about the knots? Yeah.
So is it, maybe I was too slow, but these boxes in the circuit, they correspond to the crossings in the knot diagram.
Yeah, roughly. Yeah, in this direction. Yeah, yeah. Certainly, that's the intuition. Yeah.
Then it's kind of like regularize a crossing in one of two possible ways, and then this gives the outputs. Is it like that?
I guess I just think of each of these braids is like in the TQFT, there's some unitary action of each of these little crossings, and you're kind of, that's what these U's are becoming. Yeah. So in some sense, this is the easy direction in some sense. Yeah.
I don't understand how to turn this. I mean, somehow a crossing corresponds to an isomorphism given by the braiding.
Yes.
In your
yes.
And I don't understand how to turn that into a yes or a no.
Oh, that's,
Because
you have to do measurement.
the
It's
output-
only when you do measurement that you are interpreting. You have to measure the output of the circuit on some input before you can say what yes or no is. I'm being a little vague here, but this problem, I give you a quantum circuit and I ask, okay, what-
okay.
if that's the input to the circuit, what's the probability that the output is that?
Yeah.
That's a BQP complete problem.
So essentially, you get yes if it's the right thing that you would get. when something happens.
Well-
I mean, up to scaling and blah blah.
No, that the invariant is the numerator in this ratio, right? So like, how do you, the probability is not what the computer's outputting. The computer is outputting yes or no. So if you run the computer 100 times, you can approximate that probability. And then you can back that out to approximate this. But things get funky because of that denominator.
I guess maybe you're treating the outputs all being zero as yes, all others.
Yeah.
You're just
You're
making,
just saying that that's the yes output.
Yeah.
Yeah.
measuring all the qubits, and then you get a bit string. If if the bit string is all zero, then you say that's yes, otherwise no.
And that's a BQP problem, understanding whether that's yes or no. Okay, so let me state the theorem, and I think I'll have some time to prove it, actually. So my question is all about this backwards direction, right? Like, if we think of a topological quantum computer as a way of doing, usual type of quantum computing is using quantum circuits. It's a way of instead doing that within some TQFT in this fashion. You might ask, well, can I guarantee things about the diagrams I'm working with, or about the three manifolds I'm working with, that might be useful for algorithmic purposes? And my claim is that, in fact, whenever you can go this way, you can set it up so that this diagram is a diagram that isn't one of these two things. And therefore, it's always hyperbolic. And so you can interpret that as therefore saying that the hyperbolicity won't help you for algorithmic reasons, for algorithmic applications. But let me just write that instead of saying it. So okay, so what I'll do is I'll fix like a Reshetikhin derived TQFT, Z, and an object X. And let's just say it's simple. So this is, I guess I'm conflating the TQFT with the tensor category and picking a simple object. So then my claim is the following. There exists, maybe stress, a classical polynomial time algorithm that converts a given knot diagram K to a new knot diagram K prime. Where K prime has the following properties. So the first is that, okay, I can't guarantee that the values of the invariants are exactly the same because of Reidemeister 1 moves changing the framing, but I can guarantee that their magnitudes are the same. So the invariant of K prime is basically, you just take the norm, it's the same as the invariant of K. So the second condition is that I can make K prime alternating. It's an alternating diagram. With minimal crossing number. So basically, K prime is guaranteed to be as small as possible within its topological type. Although I will stress, the whole point here is this K prime is not the same topological type as K. Certainly the diagrams aren't the same, but moreover, they're not even the same knot. Okay. So, and then the punchline is that this is hyperbolic. So the interpretation I have here is that what this means is anytime you can prove that this invariant, determined by Z and X is hard for knots, doing something with this invariant given a knot, like approximating this invariant, if that's hard, it will always be hard when you restrict to knots of this form K prime. Why? Well, because if it's hard for arbitrary K, any such arbitrary K, we can convert to K primes like this with a little bit of overhead, and then all these properties hold. So the intuition is that any hardness result for this ZX considered as a function on knot diagrams persist if we restrict to these particularly nice diagrams. These types of nice hyperbolic diagrams. Yes.
An example of a knot where you cannot, so like I want to ask the complementary question, can you, instead of getting a hyperbolic, what do you want to get a torus or a satellite? Because those to me are the nicer ones, not.
Yeah, that's fair. In some sense, that's nice. Yeah, that's fair. I don't expect it's possible. That's a great question, and I would conjecture it's not possible.
So you don't have an example?
No. So here's what I have in mind. If we might ask, let's look at this invariant, but only look at diagrams that like are knots that are promised to be torus knots or satellite knots. Well, okay. If we only restrict to torus knots, then and we know it's a torus knot, then they're only determined. There's only so much. So I assume computing this will be easy, restricted to torus knots. So now satellite knots are more complicated because like they are like torus knots combined with hyperbolic knots in some sense. So like maybe those aren't particularly nice, but yeah, I guess I'm not. It's a hard question to make precise, but I don't expect it to really be possible. Yeah.
There's no way out on this because that's a magnitude there. That might not be easier to compute than.
Yeah, that's fair. I actually know you can no. So I could say more. You actually know exactly how they differ. You know the phase.
Okay, so
You can compute that phase efficiently. Yeah. So yeah. Great question. Yeah.
You're often talking about knots, but I guess you could just say lengths.
Yeah, but this is a better theorem for restricted to knots.
So then my question is, what about telling apart three manifolds presented by surgery? Can you also add surgery data to?
Well, okay, so I'm not going to answer that question, but I'll pivot to a slightly related question. Is there an analog of this theorem for closed ring manifolds? Yeah,
The direction I'm trying to.
yeah, and I would conjecture that there is, and I could say more. Yeah. So I actually have there's really two theorems in my paper. I would say this is the easier one to present and prove. The other one uses what's called the curve complex and the Hempel distance. So that other one should generalize to closed ring manifolds, where instead of using Platt closures of braids, you use Haggard splittings of closed ring manifolds. Yeah, Nico.
Are you assuming that your category is strict?
It doesn't matter. It doesn't matter. It's just so what I definitely need is it's semi-simple. This is really important. Other than that, fairly minimal assumptions. Doesn't have to be unitary or anything. So I'll explain why we need the semi-simple in a second. Any other questions?
For the Jones polynomial.
Say that again, please.
What does the algorithm do?
The algorithm, you give me a knot diagram, I'm going to build you a new diagram where the value of the Jones polynomial at your favorite root of unity is exactly the same. Well, okay, it's the same, but the new diagram is an alternating diagram with minimal crossing number for a hyperbolic knot.
Any example?
Yes, I'll give you an example later. the algorithm does it. You give me any knot, I can do it. It's a sufficient algorithm, right? So I will do it for you. If you tell me what you want, yeah.
So you really mean the minimum crossing number and not the minimum crossing?
What I mean is this K prime minimizes crossing number within its equivalence class.
Crossing number is defined as the minimum number of change of crossings you can do to get a knot.
No, that's the unknotting number. That's the
But it's in
I mean, the crossing number in the diagram, just how many crossings are there?
reduced implies.
Sorry.
Alternating and reduced implies minimal crossing, so you get it for free, right?
Well, I use that.
Okay.
Yeah.
Simplest non-hyperbolic knot, tracking.
How about the unknot? I'll do you one better. All right, I'm gonna do. You want to see it? I'll show you how this happens. So, you know, I will do it a very explicit construction. I'll apply it to the unknot. We'll get a hyperbolic knot that has the same Jones polynomial evaluation up to this phase. In fact, it'll be the same on the nose. But the new thing is alternating and hyperbolic. So I will give you a very explicit. But let me. There's really just one ingredient, and then it's just understanding some, like, combining one ingredient from quantum topology with like fairly standard theorems in combinatorial topology. So I'm basically saying I need one rather simple quantum ingredient and then one rather simple Thurston style ingredient, and just mash them together to get this theorem. Okay, so what's the proof idea? There's basically quantum topology gives me the tool, and classical topology gives me the target. So the tool. The theorem, Laplace theorem. I mean a specific version of it. So given, let's see. Well, we've already fixed Z and X, but so I'll just say there exists a T, an integer, such that if I look at what, if I braid T full twist, you know, T full twist, right? And I color this, so this is some ribbon braid. And I color this by the object X in the statement of the theorem, both strands by the object X. Well, I can evaluate the TQ of T on this, right? So Vafa's theorem tells me that if I pick T appropriately, this is the same as that. In other words, Vafa's theorem tells you anytime you see two strands in a diagram that are just kind of parallel strands with no crossings, you can insert two T crossings without changing the value of the invariant. It's the one trick. So now the theorem, now the target comes from some well, kind of understanding the Tate conjectures and some old theorems of Manasco. So I'm going to use that in a bit. But before I do, let me kind of formulate the goal, and it's really implicit in these kind of two theorems. So the first theorem is the first Tate conjecture, which is a theorem. It says that an alternating diagram, which, by the way, a diagram is alternating as if, like, when you go around the diagram, you go between over, under, over, under, over, under. So these are all alternating. No, they're not. No. This is alternating and this is alternating, but these two are not alternating. Right. These, like, if I'm here, I'm going this way, I go over, over. That's not alternating. So here it's alternating. Okay, so what Tate tells us is that an alternating diagram, which was Tate Scottish or was he Irish? I don't know. We're here in Scotland. I should probably know, right? Or was he English? I don't know. Oh, Scottish. He's Scottish, right? Cool, great. Yeah, thanks, Tate. All right. Yeah, I'm probably not even saying his name right. I don't know. Is it Tate or Tite or
John Tate, sorry.
no, T-A-I-T, like 120 years ago. Right? So he says this has an alternating diagram has a minimal crossing number if and only if it has no obvious crossings you can remove called nugatory crossings. So a nugatory crossing is one of the following form. So I have my diagram of my knot. I'm going to think of it as coming from two diagrams, two tangles that are connected like this. And the whole thing's alternating, I'm assuming. When it says if the whole thing's alternating, then, and if it doesn't have a minimal crossing number, it's because it has one of these silly things you can obviously get rid of. How can you get rid of this? Well, you can pick up B and flip it like that, and that'll resolve that crossing. You get a new diagram with smaller crossing number that's still alternating. Okay. So that was resolved in the late 80s using the Jones polynomial. So kind of a weird Ouroboros here, but keep that up there. And so the theorem I'm about to write down is kind of a variant of this Thurston's theorem. It's like a version of Thurston's theorem here for knots, just in the alternating setting. It's due to Monasco. And it actually, in fact, uses Thurston's theorem. So to prove it. So this is Monasco Thurston. So it says a minimal crossing alternating diagram meaning it's an alternating diagram where we got rid of all those. There's no nugatory crossings. This must be one of the following. The first one, the unknot. Not an unknot, the unknot, that one. Right, is that alternating or not? I don't know. It's probably better to treat it as alternating. Right. So the second is the standard diagram. And we should interpret our diagrams as living on the sphere for what I'm about to say. Of the 2p torus knot. Which just, I mean, you take a braid, you take some odd power of it, and then you take its trace over. The third is kind of the most annoying, but it's that it might be a diagrammatic connected sum. Right, you can form connected sums of knots. To get more complicated knots. But in general, seeing if something is a connected sum is hard. But if you have two diagrams, there's easy ways you can form connected sums, and there's easy ways you can detect diagrammatic connected sums. So this isn't so bad. And then the last case is hyperbolic. So now, view this as our tool, and this is what we're aiming for. We want to use this tool to convert K to a diagram K prime, where we get K prime only by padding with these twists. That just ensures the invariance stays the same at every step. We won't be able to quite do that. We'll have to do some Reidemeister 1 moves. That's where we pick up phases that make this not equal without the absolute value. But once we have that, we just have to say, well, how do we make K just by inserting these twists alternating, first of all? So we're going to do that. And then we remove the nugatory crossings, and we're left with one of these four things. And then we have to rule out the first three things. So, yeah, I guess I'll do it here.
Your hidden knot that's under the chalkboard isn't like I thought. Like that looked like that's some extra weird stuff on it. I thought you were gonna like be like, here it is.
Oh no, sorry. I guess everything I'm going to do, I could do to that diagram, but I won't. Yeah. Okay, thanks. So so I'll approve the theorem. So step one. So given K, prepare K prime. Maybe I'll call it K1 by inserting twist. maybe we call these Waffe twist. And applying Reidemeister 2 moves. To get an alternating diagram. So let me explain what I mean by that. So ignore Waffe twist for a second. There's a really easy way to make any diagram of a knot alternating. You pick a starting point, you start walking around the knot, and it's going over, under, except sometimes it doesn't. And anytime it violates over, under, you just swap the crossing and keep going. So I want to do something like that, except I can't. I have to use these Waffe twists. So it's not that hard though. So, so here's the idea. So imagine I'm going along and I go over, and then I go over again. I want to fix that and turn that into an under. So what I'll do is I'll modify this diagram by adding a bunch of these twists here in this region. So when I do that, and I have to get the sign right. So I'll just assume T is 1 for this. So if I replace this with this and otherwise keep everything the same, well, all right, that's still not alternating. Now I go over, but what can I do? I can apply a Reidemeister 2 move right there. So this becomes, you know, I can resolve this now, get that. So effectively, I've swapped this crossing with its inverse by applying this twist and then a Reidemeister 2. So yeah.
Sorry if you already said this, but there's a theorem that tells you that this T is easy to calculate.
The T only depends on Z and X, which are fixed constants at the beginning of the calculation.
Okay.
So, yeah.
These must get to unity, I suppose.
The theorem works whenever Waffe's theorem works. So maybe I do one unitary or something, but or maybe just semi-simple. Just I don't know. Whenever I can do this trick, the theorem works. So that's step 1. Now the problem is the new diagram may not be minimal crossing, so you remove the negatory crossings, and that's easy. You can do that in polynomial time. It's easy enough. You can do this trick in polynomial time. Because anytime you would normally want to switch just in the silly way to make the diagram alternating, you have to pad with these twists, so you pick up like, you know, it's a linear time algorithm. And then the last step, we want to rule out cases 1, 2, and 3. And the way we do that is just with more padding. So now I'm going to answer Joel's question. I'm going to give you what if we apply steps 1 and 2 and the diagram we're left with, we're guaranteed it's one of these 4 things. What if it's the unknot? Well, that's not hyperbolic. We're screwed, right? Except we just pad it some more. So what I'll do, I'll think of the unknot as the following. Right? If it's the unknot, well, I might as well assume it's that unknot. Right? And now I'm going to insert twist. I put 2T twist here, minus 2T there, 2T there. By construction, its invariant will be exactly the same as the unknot, and it's alternating, and you can check it has no negatory crossings, and it's not exactly equal to the unknot. It's not exactly equal to a torus, that standard torus knot. It doesn't have, it's not a diagrammatic connect sum, so it must be hyperbolic. So that's the proof of the theorem, and I'll stop there.
I guess all you need is a ribbon category.
Yes, yeah. I don't need modular, but yeah, I would be interesting a version of this for closed manifolds.
Yes. Okay. Any ribbon category has Waffe's theorem.
Right. Any semi-simple ribbon category.
Yes.
Yeah. Right.
So the conditions again, the ones that were in the.
Oh, yeah, here. So it's important that in cases 1 and 2, it means the unknown. Or that it's either exactly that diagram, or it's not one of those because it's a connected sum. And this is not a diagrammatic connected sum. This is not a diagrammatic connected sum. I didn't really say what that meant, but it's.
I guess you asked a question and the answer is no.
In the middle of the talk, is hyperbolic geometry useful for topological quantum? No, I would argue this says no, because any topological quantum computation you're doing, you're computing, you're approximating these invariants, at least, in the classic version of topological quantum computing. And what I'm saying is, well, you might as well be approximating the invariants on these really nice diagrams. Maybe they're not nice. I don't know. They are hyperbolic though. So, and because in general, approximating the invariance is hard, it's still going to be hard on diagrams like this. So I don't expect, like, you might conjecture, oh, maybe if it's hyperbolic, then approximating this can be done in P. Well, that would prove BQP equals P. So that's the kind of thing I'm saying doesn't.
At the very beginning, you said that every node is either torus, satellite, or hyperbolic, right? So can I make it not hyperbolic that used to be torus by just making connected sum with a small hyperbolic node?
Oh, right. Sorry. I probably should modify that to say every knot that isn't a connected sum. I think my theorem was not quite correct. Yeah. So I needed to assume it wasn't a connected sum.
Okay. Otherwise, it would be kind of obvious.
Yeah. Thank you. Yeah. So the Thurston's theorem I wrote down, the knot diagram had to be irreducible. So, which once things are part of the point of this is that once things are alternating, recognizing if it's a connected sum is easy. So you can get rid of that. Yeah. Great question.